Welcome back again. This is going to be episode number 33 of Learning by Doing MPI and part number 5 of Virtual Topologies in MPI. We're going to continue from where we left off, and that was, we wanted to talk about this example. 8.5, it says that basically assume that we have 4 processes again, 0 through 3, and then in this case, this pattern is different from what we had before. In the sense that now process 0 has 3 neighbors, and you can see that we have a repeating pattern that we said it is completely allowed, and you can do that. So process 0 has 2 neighbors. The first 2 neighbors has 3 neighbors, but the first 2 neighbors are repetitive. It's process 1 and process 1. And then process 1 has 2 sort of neighbors, and that is repetitive again, process 0 and process 0. Process 2 has 1 sort of neighbor, and that is process 3, and process 3 has 3 neighbors, and that is process 0 and twice with process 2. And you see that this is also not symmetric, because process 2 is once in contact with process 3, and process 3 is twice in contact with process 2. And then these are sort of the information, and then we have this MPI graph topology inquiry, Vim MPI graph topology inquiry, and this is whatever we have. So we have 3, 5, 6, 9. That's the index pattern, because we have 3, and then plus 2 is 5, plus 1 is 6, and then plus 3 is going to be 9, and that is this pattern. And then the edges that we have is a flat representation of all these edges, 1, 1, 3, 0, 0, 3, 0, 2, 2. That's exactly what we have here. That's exactly what we have in this code example as well. There's no reordering allowed, and then we have this graph communicator. We pass in all those proper information that we have already populated, and then we use those, number of neighbors. We have already seen these. So probably this example is sort of something extra or cherry on top, because we have already used these functions. For example, we know how to use graph_dim_get, we know how to use graph_get, and print some information with that. So MPI CC, MPI. So we're not going to spend too much time on this, because we already know how it works. It should be with 4 processes. I'm not sure how many processes we used last time. Right here, and it says that we have 4 processes, again 0 through 3, and then we have 9 edges in this case, not 6 like the previous example we had. And here we have a different sort of index pattern, and we have a different edge sort of array or pattern. There we go. And these are exactly the same information as we have printed right here. Then there's another example which I just put X on it. It's not an X, but we don't care about this one. So it says MPI disk graph neighbors count, and MPI disk graph neighbors provide adjacency information for distributed graph topology. There we go. We have MPI disk graph neighbors count. That's the cousin of MPI graph neighbors count. It only works again with MPI disk graph create, and then I put a star here. It means that because we had 2 versions of this disk graph. One was this disk graph adjacent, the create adjacent, and the other one was the normal disk graph create. In the first case, we said the adjacent version basically says all the incoming and outgoing connections, or all the incoming and outgoing edges in the graph that you have. But in the general version, you have flexibility to basically try to say whatever edge you want to say between any processes. So that's the most general case we have. But in both cases, you can use this MPI graph neighbors, disk graph neighbors count. You got to pass in your communicator, and then what you're going to get is in degree, out degree, and weighted. And you see that weighted is sort of a logical variable right here. If you take a look at the C binding, you see that weighted is an integer. It's not it's not an array, but it's just a single integer, because it's going to be false if MPI unweighted was supplied during creation, or true otherwise. Okay, for this one we have MPI disk graph create adjacent. Let me take a look at my notes. Okay, let's take a look at it. Swim MPI dist graph create adjacent. Oops. .c. So this is the example we have looked at before when we were talking about this dist graph adjacent constructor. And what we're going to use here is this thing here, the count. So we have number of sources, number of destinations, and we pass in number of sources, number of destinations, and we pass an MPI unweighted here. So this means that we don't care about this weighted right now. But we could have also made like a weighted thing here. I'm gonna do it after this. So let's do it with this MPI unweighted so that you see the effect. So why didn't I use in degree and out degree just like the standard? Because for the construction of this MPI dist graph created JSON, I already used in degree and out degree variables. So that is why I used num sources and num destinations. That's the only reason why I didn't try to be consistent with what the standard says, because in the constructor we already have those incoming and outgoing sort of connections or edges. So again, similar to previous versions that we have a neighbors count, we also have a cousin of that one, which basically is without that count. It provides you extra information. You pass in your max in degree, and then it's going to give you the sources and source weights. This is going to be outputs. And then you pass in your max out degree, which is that out degree you get from the MPI dist graph neighbors count. You pass in that one, and then you're going to get your destinations, and you're going to get your dest weights. This is what we did right here. We have proper sizing with number of sources, proper sizing for destinations with number of destinations. These two are the things that we got from this dist graph neighbors count. And then we pass these two. We haven't initialized them, but we pass them into this MPI dist graph neighbors. And also notice that here we haven't passed in any weights. So we only passed MPI unweighted and tried to print some information about, for example, source neighbors and destination neighbors. We haven't printed anything about those weights here because we passed an MPI unweighted. This means that we don't care about those weights in both of sort of these function calls for inquiry function calls, let's say. So let's do that MPI cc MPI dist graph create adjacent .c. And how many processes was that? Was it 4? I'm not sure. Yeah, it was 4. So now you see that it says proc0 has 2 sources, 1 and 3, and has 2 destinations, 1 and 3. And you can see that this is exactly what we print here. It has this many sources, and then you have 2, I don't know, backslashes or forward slashes. I always mix them up. But these are the information basically printed there, right here. So now let me show you if I wanted to pass in this int weighted. So right here, I could have gone here, and instead of this MPI unweighted, I could have passed in the address of this weighted. And then I could have passed in, since this is a logical sort of variable, I could have put an if statement here. If my rank equals to 0, only the root process. And if my weighted is not equal to MPI unweighted, or actually, I'm sorry, because it says false, right? So it should be not that. It should be not 0. Because false is going to be 0, right? So then you printf that, let's say, your graph is weighted. Just like that. So if I do MPI CC and MPI run this, then you see that it's printing that your graph is weighted. And indeed, it is weighted because when I was in this switch statement, when I was doing everything here, and when I was having this constructor here, I didn't pass in MPI unweighted. Indeed, I passed in source weights and I passed in dest weights. But in this case, I use one for source weights and also for dest weights. But it doesn't mean that it's MPI unweighted. So that is, but you can still pass an MPI unweighted in this inquiry function. It means that you don't care about those weights. And if you do care about those weights, then you need to have also proper sizing for those. Since you have source weights and dest weights, let's say int, we have source. I don't want to be having the same names. What names did I use here? I use source weights as they're connected. So here I use them with a underscore in between with num sources. And then I'm going to have, this is going to be destination weights with num destinations. So instead of passing in MPI unweighted here, I'm going to pass in destinations weights. And here I'm going to pass, instead of MPI unweighted, I'm going to pass in source weights. So these two are sort of arrays, so you don't need to send them by address. And here I need to add some printing statements. So I'm going to copy that. I'm going to paste it right here. Put in space right here. So here we said proc something has this many sources, and then we print the sources that we have. And we want to say with following weights. Yeah, let's say we want to print that. Then I'm gonna take this out. There's a space there, and then we're gonna say with num sources -1, but here we want to have not source neighbors, but source weights. And the last thing on the line should not be source neighbors again, it should be source weights. And yeah, with following weights, or with the following weights. And I can do the same thing for destinations as well. So I can copy these lines before we jump out of this with this print backslash or /n. I can say with the following weights again, but instead of num sources, I should use num destinations. And instead of source weights, I should use destination weights, just like that. Whoops. And finally, here as well, it should be destination weights. And for this one, it should be num destinations -1. And if I do that, then let's take a look at what we're going to get. Okay, it's a little bit, too much information is getting printed to the console, but it works because it says that proc0 has two sources, 1 and 3, and those, they have the corresponding weights, 1 and 1. And they have two destinations, 1 and 3, with the following weights, 1 and 1. Now you see that all those weights are basically 1. This is what we supplied there. But now you kind of understand that how you can work with these two functions, MPI disk graph neighbors and MPI disk graph neighbors count, which we use it here. I kind of messed up with my example, but I don't know whether I want to keep these changes or not. Let's keep them for now. Maybe I'll change them for later because this sort of looks a little bit messy, but yeah, let's keep them for now. We're going to go to, okay, we already talked about this MPI disk graph neighbors. Oh, I did have one example for this one, and I probably forgot it. I had it in MPI disk graph created JSON extra. Let's take a look at it. MPI disk graph created JSON extra. Oh, holy moly. Yes, I did have exactly the code that I've written right now. I did have it in this extra version. So let me go back to that MPI disk graph adjacent.c and let me remove these changes that I made here, because I thought that I didn't do these things. You have to go back. MPI unweighted, MPI unweighted, MPI unweighted. I don't need those weights. I don't need those weights. And then I don't need also weighted. MPI unweighted, and I don't need weighted. Yes. So this is the original version that I have. But this in this MPI, I can run it again, but it's essentially the same thing that we had in this extra. So you see that, again, the same information is getting printed here, that we have two sources, 1 and 3, with source weights of 1 and 1. We had two destinations, 1 and 3, with des weights of 1 and 1. So I should have continued to this sort of inquiry function so that I remember what I had in my examples. Okay, so anyways, it's all good. And then these calls are local, you know, the number of edges. Yeah, you can read these. There's probably the important one is multiply defined edges are all counted with returned by MPI disk graph neighbors in some order. If MPI unweighted is supplied to source weights and des weights or both, or if MPI unweighted was supplied during the construction of the graph, then no weight information is going to get returned into that array or those arrays. And then if the communicator was created with MPI disk graph create adjacent, then for each MPI process in communicator, then order of the values and sources and destinations is identical to the input which was supplied to in the creation call. And then if the communicator was created with MPI disk graph create, then the only requirement on the order of values of sources and destinations is that the two calls to that routine basically should end up with the same sequence of edges being printed. And then, yeah, we don't care about those stuff. The next thing on the line is Cartesian shift coordinates. If the MPI process topology is a Cartesian structure, an MPI send receive operation may be used along a coordinate direction to perform a shift of data as input MPI send receive takes the rank of a source MPI process for the receive operation and the rank of destination MPI process for the send operation. If the function MPI shift is called for a communicator with an associated Cartesian topology, it provides the calling MPI process with the above identifiers, which then can be passed to MPI send receive. So the user specifies the coordinate direction and the size of this step, positive or negative, but not zero, in which that it wants to displace, basically. The function is also local. So it might sound a little bit complicated with this Cartesian shift or MPI cart shift, but what essentially it does is that we have seen, not directly, but we have played with, you remember when I said, like, when I put -1 for process 0, then it goes back and then finds process 8, which has sort of the coordinates of 2 and 0, 0. And then we said that happens because we have periodic conditions. So we have example of MPI cart shift. This is exactly that. You basically pass in your communicator, you pass in the direction that you're interested in. In our case, we had a 3-dimensional Cartesian grid. So we have 3 possible values, 0, 1, and 2. Then you want the displacement. Sort of displacement can be like in forward direction, positive, or in backward direction, negative, but it cannot be 0. As the standard says. And then what it basically does, it gives you the rank of source and rank of destination. So this is rank of source MPI process, rank of destination MPI process. That is what basically MPI cart shift does. The direction argument indicates the coordinate dimension to be traversed by the shift. The dimensions are numbered from 0 to n-dims -1, where n-dims is the number of dimensions. Depending on the periodicity, again, those things, is going to happen. If you have an end-off shift, then the value can be MPI prognol. But if you have periodic conditions, then, if you go off bounds, then it basically goes back and finds the proper sort of value. For example, for 0th direction, if you are going off with -1, if you are basically choosing process 0 and then you shift, for example, 1 to the left, 1 to the right in the 0th direction, which is rho major, then it for the right shift, you don't have any problems because the one to the right is going to be, it is defined, but the one to the left is not defined. But if you have periodic conditions, then it's going to be the last process in that 0th direction. So we had, let me just work with this example. So these things we have seen hundreds of times, and here we have no periodicity, and we're going to see that what's going to happen, and then we populate that with, we have now our Cartesian communicator or our ritual topology with that Cartesian grid information on top of it. And then we have, these are the same information that we have printed in previous examples as well, but we have rank of source, rank of destination, and then we use this MPI cart shift. We pass in the proper information right here. We say row shift is 0, column shift is 1, and that is because we are working with raw major systems, right? And then process 0 basically prints some information here. If I say MPI CC MPI cart shift, and if I say MPI run minus MP12 processes we need in this example, you see that it's going to say rank source is -1 and rank of dest is 4. And why is that? Is because of this, let me find it, right? This shift. We wanted to perform the shift in the 0th direction, and in 0th direction we have 3 processes, 0, 1, and 2, and we want to displace only 1. And take a look at this. If we are here, if we want to perform a shift 1 to the right, it means that this should be 1 and then 0 and 0. So that corresponds to this one, this coordinate right here, and that is process 4. That is why rank of destination is 4. But why do we have -1 here? The reason for that is if you want to shift 1 backward, 1 step backward, it's going to be 0 minus 1, it's going to be -1. So that is why we have -1 here, because it's going to be MPI proc null. So what is getting printed here is basically MPI proc null right here. And it should say basically source out of range, and it does it. It says source out of range. But it doesn't say destination out of range because destination is perfectly fine. It's not that. But on the other hand, if I go back, let's take a look at this. This is important. If I put, for example, 1 here, so now I have in my 0th dimension or direction, I do have periodic conditions. So this means if I want to shift 1 back with minus, it's not going to return -1 for me, but 1 back means that you go back to process with the maximum, how you can call it. If I have 3 processes in 0th direction, then process 2 has the maximum value, right? But it should be 2 and 0, 0. So 2, 0, 0, where is it? It's right here. It's going to correspond to process 8, right? So if I say MPI CC and MPI run, so exactly as I expected, it's giving me the rank of source to be 8. That is the process with 2, 0, 0, because we have periodic conditions in this case. So I'm going to revert this back with 0 here because I don't want to mess up with my examples. So now you kind of understand, right? MPI cart shift is going to give you rank source, rank destinations. But in the case that you have out of bounds sort of information in your Cartesian grid, then it's going to give you this MPI proc null. But if you have periodic conditions in any direction that you have, then it's going to basically calculate and compute that it's going to be which process. Of course, in the previous example, we had only 1 shift or 1 displacement, but you could also try it with 2 or 3 or whatever. Whoops, 25 minutes over. The next thing on the line is Cartesian partitioning of Cartesian structures, but probably we should continue with the next episode.